You know that feeling when you're staring at a geometry problem and it just looks impossible? Well, today we're going to crack 3 of them, step by step. And what you'll see is that even the trickiest looking shapes are built on really simple rules that unlock everything. Let's dive in.
So, here's our roadmap for today. We'll kick things off with a neat tangent quadrilateral puzzle. Then, we'll dive into the secrets of an inscribed hexagon. After that, we'll tackle a tough one and solve for some hidden angles. And finally, we'll wrap it all up into a handy geometry toolkit you can take with you.
All right, first up, we've got problem 68. I like to call this the tangent quadrilateral puzzle. It's a fantastic warm-up to get our geometry brains fired up. Okay, so what are we looking at? We've got this quadrilateral, A, B, C, D, and there's a circle sitting perfectly inside it, touching all 4 sides. We know the lengths of 3 sides, but that 4th side, CD, well, that's the big question mark. So how are we going to find it? Now, before we start plugging in numbers, just think about this. Most of the time in geometry, there is a single key, one little rule that just blows the whole problem wide open. Any ideas what the key is for this one? And here it is. This is our golden ticket. The theorem simply says that if you draw 2 tangent lines from the same point to a circle, those 2 lines will be equal in length. This one simple fact is about to make this whole problem incredibly straightforward. So check out how this one theorem completely dismantles the problem. As you can see in step 1, this rule applies to every single corner. The tangents from point A are equal, the ones from B are equal, and so on for C and D. Now here's the really cool part this leads to in step 2. It means the sums of the opposite sides have to be equal. So AB plus CD is the exact same as BC plus AD. Once you know that, the rest is just simple algebra. We just plug in the numbers we know, like in step 3, do a little bit of math, and solve for our missing side. And boom, the answer is 21 centimeters. See? What looked kind of complicated was really just hiding one powerful but simple theorem. Okay, 1 down, 2 to go. Let's keep the momentum going with our next challenge, problem 69. This one's all about a regular hexagon sitting inside a circle, and we're about to uncover a couple of its geometric secrets. All right, here's our next setup. We've got a perfect regular hexagon tucked inside a circle, and there's a tangent line, PQ, just skimming past it at point D. Our job is to find 2 different angles. First, one of the hexagon's interior angles, BCD, and second, the angle made between the hexagon and that tangent line, PDE. Let's tackle that first one, angle BCD. You know, this part is actually more about the hexagon itself than it is about the circle. And this is where knowing a really useful formula for polygons is a total game changer. For any regular polygon, just take the number of sides n, subtract 2, multiply that by 180, and then divide the whole thing by the number of sides again. So for our hexagon, that's 6 sides. We just do 6 minus 2 times 180 and divide it all by 6, which gives us a nice, clean 120 degrees. And just like that, angle BCD is solved. Okay, now for part 2, finding angle PDE. For this one, we've got to pull another powerful tool out of our geometry toolkit. This is a real classic for any problem that involves tangents. It's the alternate segment theorem. So let's put this theorem to work. What it tells us is that our target angle, PDE, is going to be exactly equal to the angle created by that same chord, DE, way over on the opposite side of the circle. In our case, that's angle DAE. So if we can figure out angle DAE, we've got our answer for PDE. So how do we do that? Well, look at step 3. Since it's a regular hexagon, that arc DE is just 1/6 of the entire 360-degree circle. So the angle it makes at the center has to be 60 degrees. And now for the magic, in step 4. The angle at the circumference is always half of the angle at the center. So angle DAE has to be 30 degrees, which means our answer for PDE, as you see in step 5, is also 30 degrees. And now for our final problem, number 7D. I'll admit, this one looks the most complicated, and it's even got a little trap hidden inside. But don't you worry, we're going to see right through it. Here's the situation. We're given 2 angles to start. Angle EBA is 33 degrees, and angle EAC is 82 degrees. Our mission, should we choose to accept it, is to find 3 other angles, BAC, BOC, and ODB. Okay, everybody, stop. Look at this closely. This is so important. The text explicitly tells us that lines AB and CD pass through the center O. That means they are diameters. But if you just glance at the drawing, it doesn't really look like it, does it? This is a classic test maker's trick. The number one rule is always trust the written information over a diagram that might be misleading. This one fact is the key to the whole thing.
So the main tool we're going to use to unravel this mystery is another one of the all-time great circle theorems. Angles that are subtended by the same arc are equal. Let's see how it works.
Okay, let's break this down like we're solving a puzzle, one piece at a time. First, let's focus on arc AE. It creates the angle EBA, which we know is 33 degrees. Now, follow that same arc with your eyes over to point C. It makes angle ECA. So angle ECA must also be 33 degrees. Now let's do it again. Look at arc EC. It creates that 82-degree angle EAC. What other angle does it make? Way across the circle, it makes angle EBC. So EBC also has to be 82 degrees. Okay, now we can find our first answer. Look at the little triangle OAC. OA and OC are both radii of the circle, right? So it's an isosceles triangle. That means angle BAC has to be the same as angle OCA, which we just figured out is 33 degrees. That's answer number one. For the next one, angle BOC, we use another classic rule. The angle at the center is double the angle of the circumference. So BOC is just double BAC. 2 times 33 is 66 degrees. 2 down. For the final piece, ODB, we bring it all home. Angle AOD is vertically opposite to BOC, so it's also 66 degrees. Now we're just looking at another isosceles triangle, AOD. Its top angle is 66, so the other two base angles have to add up to 114 to make 180. Split that in two, and our final answer, ODB, is 57 degrees. We did it.
And there we have it. We cracked all three problems. Now let's take a moment to recap the super powerful tools we used so you can officially add them to your own geometry toolkit. So let's quickly review the keys to our success today. First, the tangents from the same external point are equal, which gave us that awesome shortcut for quadrilaterals. Second, know the basic formulas for your polygons. It's a huge time saver. Third, the alternate segment theorem, an absolute must-know for tangent problems. And finally, the dynamic duo of circle theorems. Angles from the same arc are equal, and the angle at the center is double the angle at the edge. You master these, and you are ready for anything.
And that's a wrap on our geometry session. We've proved that every complex-looking problem just has a key waiting to be turned. So the only question left is, which of these tools are you going to use to absolutely ace your next test? Good luck and happy solving!